Hi everyone. Let us see about the kinetics of sterilization. So the destruction of microorganisms by means of steam or moist heat is described as a first order chemical reaction. So how this first order chemical reaction can be represented? It can be represented as minus dN by dt is equal to Kn. What is this N? N is nothing but it's the number of viable organisms present. And what is T? T is nothing but it's a time of sterilization treatment. That is how much amount of time is needed to sterilize the particular, it may be a medium or ferment or anything else. Okay. And what is this K? It's a rate constant of the reaction. Or the specific death rate. Okay, so this is the first order reaction. Any destruction of microorganism by means of steam is a first order reaction, and you can write it with the help of the equation minus dN by dt is equal to Kn. And N is nothing but the number of viable organisms present. T is the time of sterilization treatment. K is reaction rate constant of the reaction or the specific death rate. Okay, so now let us go to the next step. That is, you should consider the total number of organisms present. That is the total number of organisms present in the volume of medium to be sterilized. Total number of organisms. Okay, total number of organisms you are going to take, not the concentration, not the concentration of the medium. You are going to take the total number of organisms present in the volume of the medium that has to be sterilized, which is to be sterilized. And minimum number of organisms to contaminate a batch is 1. Take the minimum number of organisms to contaminate a batch is 1. That is, one presence of one microbe itself can spoil the whole fermenter. So take it as 1. Okay, regardless of the volume of the batch. Don't need to consider about the volume or concentration, etc. Just leave that. Take the number of organisms present in particular media to be sterilized. Now you can integrate the equation 5.1. That is, you have to integrate this equation minus dN by dt is equal to Kn. If you are when you are integrating, you will be getting Nt by N naught is equal to e raised to minus Kt. So what is this N naught? So N0, 0 means initial stage. So N0 is nothing but is a number of viable organisms present at the start of the sterilization treatment. And NT, number of viable organisms present after the treatment. That is after a time period T. So it is the time period. T is nothing but it starts from initial to last. That is after the completion of the whole treatment. While you are taking the natural logarithms, you can see ln nt by n naught is equal to minus kt. The exponential can be that is, it can be nullified with the help of natural logarithm. That is, you have to use the natural logarithm. So you will be getting ln nt by n naught is equal to minus kt. And now the graphical representation, it's represented in two graphs from which it can be seen that the viable organisms that declines exponentially over the treatment period. That is, when time increases, first consider about 1,000 organisms is being present in a media. While the time increases, while you are giving sterilization treatment, while the time increases, the number of organisms would get decreases. Okay, so over the time increases, the number of microorganisms will decline. A plot of natural logarithm of n by n naught against the time yields a straight line, the slope of which equals to minus k. You can understand by seeing the graph. Here's a graph. That is, it's a time. So nt by n naught and ln nt by n naught. Here the number of microorganisms present at the initial stage. When the time increases after sterilization, the number of microorganisms is getting reduced. So it is a curvical graph. Here you can see after taking the natural logarithm, a steady decrease in the presence of microorganism, and the time increases, and also the sterilization treatment increases. Okay, so here You can see a value of nt is less than 1 is considered in terms of the probability of an organism surviving the treatment. That is, sometimes a microorganism may escape. So you have to consider the value as 1. Okay. For example, if it were predicted that a particular treatment period reduced the population to 0.1 of a viable organism, this implies that the probability of one organism surviving the treatment is 1 in 10. 1 in 10. That is, if you want to express it in practical terms, means one batch in 10 becoming contaminated. Okay. So the value of K is not only species dependent but also depend on physiological form of the cell. For example, the endospores are very dangerous one. They are very heat resistive one. So a lot of heat is needed if bacillus is present in a vegetative form. So bacillus is present, then vegetative cells. That vegetative can be easily sterilized when comparing to the spore form of a bacillus. So spores are very dangerous one. And effect of the time of heat treatment on the survival of a population of bacterial spores. Here you can see about that. Derivation from an immediate exponential decline in viable spore number is due to the heat activation of the spores. That is the induction of spore germination by the heat and moisture of the initial period of the sterilization process. Here you can see the destruction of spores during the early stages of the process, and therefore viable numbers increases before the observation of exponential decline. That is, destroying the spore is very difficult one. Sometimes some spores of the bacillus or any other bacteria can remain in an fermentation media. That also has to be sterilized. So an activation that is balanced by spore death. Here you can see in the picture. First ln nt by n naught, as the time increases you can see a curvicle, that is a decline in the growth of microorganism. In the same, in 5.2b also you can see an activation balanced by spore death, the death of spores. Here initial population decline at a sub-maximum rate during a sterilization treatment due to the death of spores being compensated by the heat activation of spores. Here in this picture you can see the that is in the two diagrams, that is in the two graphs you can see the death of whole culture, that is both resistive organism and sensitive organism, how it respond to sterilization, that can be seen in this two graph. Here this is a time versus ln n, and also here is also time versus ln n. Here you can see the dotted as whole culture and a single line as sensitive organism, and a long dotted graphical representation is resistant organism. So you are going to first give sterilization treatment. While a large amount of cell is present, you are going to sterilize a particular media. So while sterilization, the sensitive organism began to die. Okay, the sensitive organism become decline. That it happens. That is, the microorganisms going death. But at certain period, you can see a resistive organism developed. So spore formation is there. So this spore has also been eliminated. So it is very heat resistive one. You can see the difference between the time here. How much time it is lacking due to the spore formation. So this spore has also been avoided. So it takes some time doing sterilization. So this is the sterilization of mixed culture. Here also you can see the effect of sterilization treatment on a mixed culture consisting of high proportion of relatively resistant organism. This is the resistant organism is here. So this has to be avoided. You can see sensitive organism dies within a short span of time. But how much time this particular resistant organism is taking? So this resistant culture is when it is death only, you can see the whole culture is being sterilized. Otherwise you can't see the whole culture is being a sterilized one. and you can use it for fermentation. You cannot use when the spore is present. So it should also be eliminated by continuous sterilization methods. So these are all about the kinetics of sterilization methods. Hope you all understand the video. If you like the video, kindly like, comment, share, and subscribe the video. Thank you.